So last time we talked about the significance of the equilibrium constant KEQ. We can do some calculations involving KEQ, and there's a couple main types. So in one of them, like in example 17.1, you're given the concentrations, equilibrium concentrations of all the substances involved in the reaction. We take those equilibrium concentrations and plug them into the equilibrium expression and calculate K. So let's take a look at the wording here. It says some nitrogen and hydrogen are placed in an empty 5.00 liter container at 500 degrees Celsius. So temperature does not affect how we set this up. Remember that K's value depends on temperature. So at 500 degrees Celsius, it has a certain value. At a different temperature, it has a different value. When equilibrium is established, 3.01 moles of nitrogen, 2.10 moles of hydrogen, and 0.565 moles of ammonia are present. Evaluate Kc, that means calculate Kc for the following reaction. So what's important to note is that you need to write your equilibrium expression from the equation as given to you. So in this case, if we look in the top of page 665, we see Kc equals concentration of ammonia. So ammonia is our product, even though we know it's the reactant of the reverse reaction. Concentration of ammonia squared over concentration of nitrogen times concentration of hydrogen cubed, and those again exponents come from the coefficients in the balance equation. Plug in our equilibrium concentrations into the equilibrium expression, and that will give us our equilibrium constant. So now we're a little bit out of order in the notes here, so go ahead and turn the page in your notes and go to page 694 and work on practice problem number 25. It's very similar to that last example. We're just plugging in equilibrium concentrations into our equilibrium expression. So go ahead and pause and do that now, please. All right, so we'll start with our equilibrium expression. I just write K equals, put KEQ, KC, whatever you want there. I plugged in my concentrations. Looks like each of those numbers has two significant figures, so our answer will have two sig figs, and we end up with this value. So remember that even though we're using concentrations, we don't plug in units into our setup, nor do we get units then for K. So we just express it as a number. All right, follow-up question. Based on the value of K, is this reaction reactants favored or products favored? What is favored at equilibrium, reactants or products? Go ahead and answer that now. All right, since the value of Kc is much less than 1, then we can conclude that the reactants are favored at equilibrium, meaning there's a lot more reactants at equilibrium than there are products. All right, let's take a look at the next one. Go back a page. Sometimes, instead of given the concentrations of each of the substances at equilibrium, we're given the amounts or concentrations, say, before the reaction starts. If this is a case where maybe we're given K, so if maybe you're given the value of the equilibrium constant, or definitely when you're not given equilibrium concentrations, you're given, say, initial concentrations, this is your sign that you're going to use ice. So be careful, make sure you know when to ice and when not to ice. So obviously on that last problem, we were already given equilibrium concentrations, so we just plugged those in. We didn't need to use ice, but sometimes you do. So it says if you're given initial amounts, so that could be, actually could be more than one thing. Could be amounts in moles, could be concentrations, could even be pressures of gases. And you're asked for the amounts at equilibrium. So again, equilibrium concentrations, equilibrium pressure, something like that. You must use an ICE table. So ICE stands for initial concentration, change in concentration, and equilibrium concentration. So let's take a look on page 665 at 17.2. Read along with, and let's see how this is different than the last problem. We put 10.0 moles of N2O into a 2-liter container at some temperature where it decomposes according to the following equation. So notice we're only given the amount of one substance or one reactant. We're given the amounts at the beginning. That's definitely not our equilibrium amount. Then it goes on to say at equilibrium, 2.20 moles of N2O remain. Calculates the value of Kc for the reaction. All right, take a look at the solution. Again, in our ICE table, you have a couple choices here. You can use molarity or moles. Here's the problem. If you decide to use moles in your ICE table, you cannot plug moles into an equilibrium expression. You need to plug in concentrations. So you would have to convert all of those equilibrium amounts in moles to molarity or moles per liter. So in the book, what they do is they first converts the initial concentration to molarity. So we have 10 moles in a 2-liter container. That's 5.00 molar. How much nitrogen and oxygen do we have at the very beginning? We have none of that. And the question makes no mention of any nitrogen or oxygen to start off with. So it's important that you fill these out in your ICE table. Those are 0 initial concentrations. And then there's something else given to us that allows us to fill in more of our ICE table. We're given the amounts of N2O at equilibrium. It's 2.20 moles are still in a 2-liter container, so the equilibrium concentration is 1.10 molar. Let me write this out just to show you what I'm expecting in your setups. So I'm okay if you don't put units in your ICE table, but in your final answer, you'll want to put units. So we're given the initial concentration, we're given the we're given the equilibrium concentration. We need to find the change in concentration. Technically, to determine the change in concentration or the equilibrium concentration, we use this. The initial concentration plus the change in concentration equals the equilibrium concentration. Well, a couple things also important to note is that the amount of the reactant or reactants will decrease during the reaction. So we're going to put a negative there in the C row. And then the amounts of the products or concentrations of the products are going to increase. So for our N2O, if you start off with 5.00 molar and ended up with at equilibrium 1.10 molar, that means the concentration went down by 3.90 molar. Once we know the change in concentration of one substance, we can use that number along with the mole ratios to determine the change in concentrations of the other substances involved in the reaction. So here's what we're going to do. Oops, I didn't balance this equation correctly. Let's put a 2 there in front of N2. Notice that the mole ratio of nitrogen to N2O is 1:1. So however much the N2O goes down by, the N2 will go up by the same amount. However, notice that for oxygen, we have a 1:2 mole ratio, meaning that the oxygen is going to go up by half the amounts that the N2O goes down by, or half the amount that the N2 goes up by. Either way is fine. You can compare whichever gives you an easier ratio. So I'm going to write it like this initially. The book has it as the actual value there, 1.95 molar, which is fine. Actually shows a little of both. And then we can use I plus C equals E to get our equilibrium concentrations. So 3.90 molar for the N2 and 1.95 molar, molar for the O2. Now, if you're asked to give the equilibrium concentrations, I'm going to ask that you take those numbers out of the ICE table and then write their answers off to the side. So for example, equilibrium concentration of nitrogen, 3.90 molar, equilibrium concentration of oxygen, 1.95 molar. Now that we have the equilibrium concentration of each substance, plug those into the equilibrium expression. And you can see that at the bottom of page 665 and calculate our value of K. Notice K is larger than 1. That means the products are favored at this particular temperature. All right, go ahead and practice one of those. Number 27 on page 695. A little bit different, just to warn you. So a little bit different because we're not calculating the value of K. Let me take a look and make sure I'm giving you the right problem to work on. So this time we are given the value of K, and we're going to use that to find some concentrations. So I'm going to give you a chance to try to work that out. Pause the video, and I'll show you the setup after you've had a chance to try it out on your own. Pause now. All right, let me walk you through a bit, see how you did in comparison. So this is with the information given to us in the problem. So we're also given the value of k here, but I just wrote the equilibrium expression just with a letter k. But we'll plug in that value that's given to us. And so question is, what the heck do we do? We're not given anything else. We do know this, the amount or concentration of CO is going to decrease, as will the water, and the CO2, whoops, I wrote something wrong here. That's H2. Can't have H2O twice in there. So let's fix that. Sorry about that. That looks better. The H2 concentration is going to increase as well. So question is, how much is the concentration of each substance going to change by? Unlike the last problem in the book, we are given some additional information such as the amount of one of the substances at equilibrium, which we can then use to find the change in concentrations. We don't have that information here. So this time we're going to use a variable. So since everything has a 1-to-1 ratio, everything's concentration is going to change by the same amounts. So equilibrium concentration of CO, 0.500 minus X. Same for the water. Equilibrium concentrations of CO2 and H2 are each X. We're going to take that, plug it into our equilibrium expression. So we get X squared over 0.500 minus X squared equals our Kc, which is given to us in the problem. It is 1.845. And I guess the question for you is, do you want to solve this the easy way or the hard way? So we're going to, if we factor out that bottom there, we're going to end up with a quadratic equation, and we need to use a quadratic formula to solve for x. There's an easier way. See if you notice it. What's an easier way to solve for x? Well, we could do this, couldn't we? Square root both sides. I think that'll greatly simplify our setup. So go ahead and square root both sides. So we get x over 0.50 minus x equals whatever the square root of 1.845 is, and then solve for x. Go ahead and pause the video, solve for x, and give the answers. Answers are the concentrations at equilibrium for each of the 4 substances. Go ahead and pause now. So solve for x, we get 0.288, and then plug that in here to get the concentration of CO and H2O, which is 0.212 molar. And then, of course, X is the same as our concentration of CO2 and H2, so that's 0.288 molar. So this is a common type of calculation, especially with acids and bases, where we are given the value of the equilibrium constant, and we need to use that to find, like in this problem, X, some sort of X. All right, so let's take a look at how we can manipulate KEQ. Just make some calculations a little bit easier instead of having to redo the whole equilibrium expression. So it says, if an equation with a predetermined equilibrium constant is multiplied by some factor, so you double an equation, you triple an equation, then the new KEQ is equal to the old KEQ raised to the power of the multiplication factor. If you don't believe me, take an equation, balance equation, write the equilibrium expression, double each coefficient, and you'll see that the KEQ then would just be the square of the original KEQ. If the equation is written backwards, then the value of the new equilibrium constant is simply the inverse of the original KEQ. Again, don't believe me, try it out. If 2 or more equations with known equilibrium constants are added, then the new summed equation has a new KEQ equal to the product of the equilibrium constants of the equations that were added. Take a look on page 666 at 17.3. It says you are given the following chemical equation and its equilibrium constant at a given temperature. Write the expression for and calculate the numerical value of the equilibrium constant for each of the following at the same temperature. So looking at the first equation, letter A, that is double the original equation that we're given. And so if we do that, we're just going to end up squaring our equilibrium constant. So it goes from 4 times 10 to the fourth to 1.6 times 10 to the ninth. Letter B, that looks to be half of the original one. And so that means then we're going to raise our Kc to the 1/2 power, take the square root of that. So originally 4 times 10 to the 4.0 times 10 to the fourth. Square root of that is 2 times 10 to the second. All right, give you a chance to practice with something like that. Go ahead and go to page 695, number 31. Let's do both A and B. Similar type of problem as this last one. A and B, number 31. Go ahead and pause now. All right, it looks like letter A is the inverse of the equation given to us. So the inverse of 279 looks to be 0.00358. And then letter B, that's the same equation, but half of what we were given originally. So we're going to take the square roots. Let's see if that works. Square root of 279, and we get about 16.7.